Okay, hi everyone. Thanks for coming to another Graphs and Matroids seminar. Today we have Michael Wigal at Georgia Tech, who's going to be talking about approximating TSP walks and subcubic graphs. Go ahead, Michael.
Okay, thank you for inviting me. So as an introduction, this is a joint work between Young Ho, which I believe I saw him in the chat, and our advisor, Xing Xing. So on the left is me and Young Ho in Philadelphia a few years back, and the floating head to the right is our advisor, Xing Xing. And I guess as a quick advertisement, Young Ho is recently going to the postdoc market, so I'm just advertising that fact. So if you like what you see, maybe reach out to him. So first, I'm going to introduce the problem and maybe some of the background and history and try to motivate why people care. So the traveling sales problem is an old problem. It's given a complete graph with the weights on the edges or distances equivalently. You want to find a tour or equivalently a spanning cycle of minimum length. This is MT hard due to containing the Hamiltonian cycle problem. And it's also not possible to approximate within a constant factor unless P is equal to NP. Because if you have any constant factor approximation, you can turn this into a polynomial algorithm to solve the Hamiltonian cycle problem again by just weighting the edges of the graph in an appropriate manner. So to overcome this difficulty, this has led to the consideration of many special cases. So one nice special case is metric TSP, where you assume the distances between on the edges is follows some type of metric essentially. And this is a natural assumption for many cases, because if you're a traveling salesperson, whatever space you occupy, space typically behaves. The distance in that space typically behaves with a metric, so it's generally okay to assume. And just assuming that the distance is a metric gives a very nice 3/2 approximation algorithm by Christofides and independently by Sertikov in 1978. The independence is due to the iron current at the time. Christofides' approximation algorithm is very nice and very beautiful, and if you haven't seen it before, I highly recommend it. It's like a couple paragraphs, and it's a good example of beautiful math. And only recently has this approximation algorithm been improved by a very small constant. So I want to stress that there's been a 40-year gap just to get this small amount of improvement. And so traveling salesman problem has a notoriety. It's notorious for being very difficult. So this has led researchers to consider many special cases. One such special case is graphic TSP, where you assume that you are trying to find a spanning closed walk on a graph. And to see how this is a special case of metric TSP, for any edge not in the graph, you can add an edge with weight equal to the smallest closed walk between those vertices. Another special case is to consider cubic or subcubic graphs. A cubic graph is in which every vertex has degree 3, and a subcubic graph is a graph where the max degree is 3, essentially. And cubic or subcubic graphic TSP is graphic TSP restricted to those respective graphs. And again, both of these are special cases of metric TSP, and they also both remain NP hard because finding a Hamiltonian cycle on a cubic graph is still NP complete. But assuming you're playing on a graph allows you to bring in graph theoretical tools to try and build new algorithms. So why do you care about subcubic TSP? That seems like a very special case. Well, there's a couple of reasons. One, it still inherits the improximability hardness of metric TSP. So it's known that metric TSP is 123 over 122 improximable. Graphic TSP is slightly better, but it's still improximable with 185 over 184. And subcubic TSP is 685 over 684 inapproximable. And cubic TSP is also inapproximable with a small constant. Another reason why people care about subcubic graphs is their connection with the famous conjecture on the linear relaxation of the traveling salesman problem. So the linear program associated with TSP is called the Subtour Elimination problem. And I wrote the LP over here. But what you're essentially asking is for X is like an indicator vector for the edges with weights on them. And you want the weights at each vertex to sum to 2. And for each subset of vertices, the sum of the weights going out of that subset is at least 2. And the weights are positive. That's essentially what this linear program is saying. It's very natural. And Goleman's conjecture in 1995 that the integrality gap for subtour elimination is 4/3. That is, if you take the optimal linear program solution and round it to an integer solution, then you're only off by a factor of 4/3. I forgot to write, I should emphasize here that Goleman's conjecture is for the metric TSP. So it's the linear relaxation for metric TSP, not general. So why do people care about this conjecture? If this conjecture is true with constructive polynomial time proof, this would go to 4/3 approximation algorithm for metric TSP. And there's known families of subcubic graphs that asymptotically realize this 4/3 integrality gap. So people, I guess, these exhibit the worst case behavior. So to try and understand this conjecture better, these are kind of like the simplest worst case things you got to deal with. And for an example of such a family, you could take 3 paths of equal length and join them at their endpoints, and that family asymptotically reaches this 4/3 integrality gap. Okay. Okay. So I'm going to briefly cover the history of the approximation algorithm. So we've already seen that metric TSP has a 3/2 approximation back in the 1970s. Later on, this was broken with 3 connected cubic graphs in 2005. Again, note how many years it took. Later on, this was extended to graphic TSP a few years later. And the bound for graphic TSP was later improved to 1.461, which later on, with the proof analysis, got it to 13/9. Later on, we reached 7/5 for graphic TSP. And again, this should be 2021, but very recently, for metric TSP, they were able to break through 3/2, which is quite an achievement. This covers graphic TSP. The next slide, I'll help to talk about subcubic TSP. So in 2005, we've already seen that they were able to break through the 3/2 boundary with cubic graphs, 3 connected cubic graphs. Later on, motivated by Goleman's conjecture, Agrawal and Gupta were able to get a 4/3 approximation for 3 connected cubic TSP. This was later extended to 2 connected cubic TSP. And quickly after, all these results came out very, very similar. So I don't know the exact ordering, but they also got a 4/3 approximation for 2 connected subcubic TSP. Okay, and then later on, they were able to break through the 4/3 boundary by a small constant, 4/3 minus 1 over roughly 60,000. Later on, a year later, they were able to prove it by a bit more. Later on, they got to 1.3 approximation. Dvorak, Kral, and Wahar in 2016 were able to get the 9/7 approximation for 2 connected cubic graphs. And finally, this is where our result lives when we got a 5/4 approximation for 2 connected cubic TSP. So it's been I guess, a long road to get here. Fine. So I think now we understand the context of where this result lives. I'm okay with introducing the main result. So our result says, let G be a simple 2 connected subcubic graph on n vertices, and we let n2 with a subscript denote the number of vertices of degree 2. Then TSPG, TSP being the minimum length of a TSP walk, or the optimal, is at most 5n plus n2 over 4 minus 1. And in the special case, if g is cubic, n2 is equal to 0, and we still get a bound for cubic graphs. And we can find such a TSP walk in quadratic time. And this was conjectured by Dirac, Kral, and Mohar in 2016. And this bound is best possible. There are infinitely many subcubic graphs that obtain this bound, and there are infinitely many cubic graphs that almost obtain this bound. And both of these families were constructed by Dirac, Kral, and Mohar in that 2016 paper. We not only prove this bound, we characterize exactly when the graphs are equal to this bound. And we can talk about that later. I guess now I should stress that the graph has to be simple. There are known families where it's not true if it's not simple. You can take 3 paths of equal length, join them at the endpoints, add some parallel edges. The optimal TSP walk for that graphs have it's 4/3 in essentially, and that does not agree with the proposed bound here. So it's important that the graph is simple. So I'm going to introduce some terminology here on even covers. So how we prove this result is we don't construct the walk directly. That's too difficult. What we find are nice even covers of the graph that we later then modify to a TSP walk. So for the purpose of this result, and for the purpose of subcubic graphs, an even cover is a spanning vertex joint union of cycles or isolated vertices. And we need some way to measure when an even cover is good. And so this is what this excess of an even cover. We define it for each cycle has weight 2, and each isolated vertex has weight 1. And I believe this concept was introduced in the Dirac paper in 2016. And they used that to get to 9/7. And we also use this, but we were able to use this idea to get to 5/4. And so minimum excess is straightforward. We define XSG to be the minimum excess for overall spanning covers, even covers. And so Dirac, Kral, and Mohar showed that if G is subcubic, then TSP is related to the min excess of G by this linear function. And the main idea here is if you have a spanning even cover, you can add edges between the components to make the graph connected, and those edges form bridges, so you would have to transverse those twice, and that's basically how you construct the TSP walk. So our goal originally was to show TSPG was this bound above here, but since that's too hard, we work with excess, so we actually want to bound the excess. So this is closer to what our main result says, is that if you're a 2 connected subcubic graph, then the min excess is the most n plus n2 over 4 plus 1. That's what we want to prove. Okay, so what's the naive way to prove this? So let's say you're given a graph G and an edge E. Can we find an even cover F containing E such that the excess of that spanning even cover is at most the bound we want? The answer is no. You can't do it. There's known constructions. For instance, I believe like K4 minus an edge, it's off by a half. So you can't do it. There's infinite many. So that ran into problems. Okay, so then the next thing we tried is like, okay, what about, can you always go find an even cover that doesn't go through the edge E? And again, no, that's not possible. You can take like passive link 2 joined by their invertices, and that graph is off by a half again. So that kind of runs into a problem. What do you do here? But what we notice here is that for a given pair GE, the 2 quantities balance out. So if one of these inequalities is bad, the other is very good. And so we essentially had to understand, like, why it's bad and how these two interact. And with that, we were able to make things work. And how we were able to make these work is we were able to characterize both extremal cases. So I guess now I should emphasize our result is very structural graph theory. I mean, it's just we characterize the structure of all these extreme cases. And since we have a good idea what they look like, we can make good decisions on building this even cover. Okay. Right, so this is closer to what our main theorem says, is that you find an even cover where the min excess is at most bound, but we can't say +1, so +3/2 is always true though. And the third statement here is saying that when we first introduced the delta hat is kind of like what's the easiest way to describe it? It's kind of like it's like the constant of how far you're off. We don't want to, for counting purposes, it's easier to think about. You don't want to care about the number of vertices in the bound. You just want to know how far away you are from the proposed bound. So this is what the delta and delta hat measure. And the delta is for when the even cover goes through an edge, and the delta hat is when the even cover doesn't go through the edge. So there's two different deltas here. And you may notice that delta has a -2 to it, and that's notation. So throughout the proof, we're going to have to piece together cycles. And for the purpose of counting, that cycle doesn't really exist. So it's much easier on the notation if you kind of just don't include that cycle in the count, because it's usually going to be taken apart and glued together with some larger cycle. And so since we understand the delta is kind of like the savings of going through an edge, and delta hat's kind of intuitively the cost of not going through the edge. And so, as I stated earlier, the third statement in our main theorem, or a rough approximation of our main theorem up above, says is that these two balance out. So if one of them is bad, you're going to save enough on the other one. Okay. So to help build intuition for what these things mean, we're gonna talk about subcubic chains, which are very important pieces of the proof, and they're kind of like the simplest things you have to be able to work with. So we'll illustrate how delta and delta hats interact with these things. So a subcubic chain is a sequence between two vertices x and y, where it's a chain of blocks, a subcubic blocks, where a block is a maximum subgraph with no cut vertex, so it's two connected. But notice, like for instance, in the picture, B2 could just be a single vertex, so that's also a block. We call these things subcubic chains. Its closure is as pictured here, as you delete x, y, and you add this edge EC, and that's for inductive purposes, because if you want to go through this chain, all you have to do is ask to go through this edge EC, and that would give you a cycle that goes through this chain, roughly. And if you don't want to go through this chain, you can ask it not to go through the edge EC. So it's a nice way to take these structures and put them into the induction. And to handle the chain, you just induct on each of the blocks. So we define what a chain block is. You do the same process. You add an edge between the two connection vertices. And we have this operation of suppressing a subcubic chain. And it's the graph where you delete the chain C and you add an edge. And again, that's for induction purposes. And notice that non-trivial subcubic chain has a two-edge cut. And so what we'll see later is that intuitively you can just think of them as edges that are weighted in a certain way, because they have a cost or savings, which is what the deltas are going to measure. All right, so we're going to introduce this proposition here, which will be a nice way to see how you do calculations with these deltas. So what this is saying, for instance, in the blue here, is that delta GC, the cost of, or the savings of going through a chain, is equal to the cost of suppressing the chain plus the cost of, or plus the savings. This is delta savings. So it's the savings you get from going through the edge GC in the suppression and the savings you get for going through the closure of the chain. And delta hat has an anomalous equation there. So how do you what's the calculation? So first you notice how many vertices you want to make sure the vertices match up. So the amount of vertices in G partition to the vertices of G suppressed C and the number of vertices in the closure, similar for the number of degree 2 vertices. And notice there's a bijective correspondence for any spanning even cover that goes through C, has a cycle that goes through C. There is corresponding spanning even covers of G suppressed C and the closure of the chain, such that they go through their respective edges, and that you can basically you cut the chain and you cut the cycle going through the chain in two, and you get two cycles with their respective graphs. And so we have that the excess of f minus 2, because we never count the cycle that goes through the respective edge, is going to be equal to the excess of G suppressed C and excess of C. And the minus 2 here is from we don't count the cycle that goes to the respective edges. Since delta GC is equal to the min excess by definition, we can split the excess as above. It carries over the minus ng plus n2g over 4. But as above, since these partition between the respective graphs, we get that it's equal to the delta G suppressed C plus delta of the closure of C. And so this is like the simplest case to try and build intuition. And so the calculation for delta hat is very similar. And so this is how the cost and savings kind of distributed. And so, right. And you can imagine that since we can calculate the deltas of going through a chain and the delta hats of not going through a chain, this allows you to choose which chains you want to go down later and so on. All right, so in other words, delta and delta hat are the differences made on the overall delta GE by going through or not going through the subcubic chain C. Okay, so here's our main theorem again. We're emphasizing that G minus E has to be 2 connected. This is specifically for that. And so if G minus E is 2 connected, we can bound the delta and delta hat in this manner. And it's the main theorem. We don't want to write min excess for convenience. Like, it's easier to just think about the deltas, about how far away you are from the ideal constant, or the ideal bound, I should say. So we're going to, for introduction terminology, if the delta plus delta hat is equal to 0, i.e. if the third inequality is tight, then we say that G is tight. And if G is tight, there's only 3 possibilities for the delta delta hat pairs, 3 to 1 and 2. And so they're written here as illustrated. They're tight and they come in increments of 1/2, and the delta and delta hats are always in increments of 1/2 because the graph's cubic. That can be argued. So what our proof will do in addition is it has to characterize when these delta are tight, and we can use that to understand the structure better, to know what we should do in different situations. And characterize all tight pairs. Okay. For when G minus C isn't 2 connected and it's 1 connected, and you're essentially the closure of some subcubic chain, then the delta and delta hats are just the summations of the respective chain blocks. Straightforward idea. Thus, if a closure of a chain is tight, every chain block is also tight. Again, should be straightforward. Okay, so one important structure here that will be one of our extremal examples is the rooted theta chain. So a rooted theta chain, GE, is the eternally disjoint union of 2 of two subcubic chains with the same endpoints as E. And a theta end chain is the internally disjoint unit of three subcubic chains, so with common endpoints. So a rooted theta chain is a theta chain where one of the theta chains is triplet, where it's just an edge, okay? And I have a rooted theta chain drawn here below. And these ideas, these definitions extend to these specific structures. So we say that a theta chain is tight if each of its chains are tight. And it's balanced if each of its chains are balanced in that sense. It's minimal if the chain is the smallest savings possible, which is -1/2. Okay. All right, so again, this is our main theorem. We've introduced enough terminology so I can make it slightly more accurate what our main theorem is. So we need to emphasize that it's simple. And if G minus E is 2 connected, then we have this. And we have for 1 with equality if and only if G, so for, okay, first of all, no one is tight if and only if G is a tight balanced rooted theta chain. And 2 is tight with equality if and only if G minus E is a minimal theta chain. Right, and furthermore, if it's for number 1 is tight if it's a minimal theta chain, so it might not be right. And for 2, it's tight if and only if E is a simple chord of a 4 cycle in G minus E. So this is just again further structure characterization. Right. And so the other tight example is -1, 1. And we've characterized it. So -1, 1 is saying that you save 1 if you go through the edge or you have a cost of 1. So that's essentially when call it the TSP bound we care about. That's essentially when the TSP bound is tight. So what we have is that if your subcubic graph is tight in this bound, then it's isomorphic to K4 or it's a minimal theta chain. There's 2 other cases here that I ran out on the slide, so I didn't write them, but they only pop up in the induction. They're just technical results of cases where there's a parallel edge. You got funny stuff can happen that pop up, but okay. And so, okay, as a corollary, the excess bound, or equivalently, the TSP bound is tight with equality if and only if G is K4 or G is a minimal theta chain. What is interesting about this result is Dvorak, Kral, and Mohar in the 2016 paper gave an infinite family for which this bound, their proposed conjecture bound, is tight. And this is the exact same family, which we later found out, which is always neat when that happens. Okay. Right. So. Right. So I'm just going to give a brief sketch on like roughly what happens here. So how can you prove 1? There's a couple cases. You check for the case where it's G minus UV is disconnected, where UV are the vertices of the edge E. If G minus UV is disconnected, then GE is a rooted theta chain. So roughly how you prove this is that what this is saying that if it's a rooted theta chain, you have to either go left or right. So you get savings from one chain and you get the cost from the other chain. And that's true for both I. And so to prove it, suppose that delta GE is greater than -1/2. Then we have that in green, just from the above equation. And so by 1 and 2 in the green equation, you can show that they're all equal to 0. So the extreme example is G has to be a tight and balanced rooted theta chain. And so that's where we get the tight balance from. Okay. The other case, if G minus UV is connected, that's a little harder. This splits into multiple cases. If E is in a 2-edge cut or has a parallel edge, it's easy. It works in the straightforward way how you would imagine it would work out. And if it's not, you have to delete UV, look into what the block decomposition of the remaining graph is. There's two cases. Either the block decomposition has two vertices degree 3, which we'll label Z1 or Z2, or it doesn't, which then it has one of like degree 4, which is C1 is equal to Z2, and then you have to do a lot more work. It's not too bad, maybe a couple pages, but basically you have to use what you know about the delta and delta hats of these chains to make the right decision of how you want to path a cycle through these two graphs. So that's essentially what very high level bird eye view of the proof for this case. For the second one, it's a little easier. The main idea is you want to now find a chain or find a spanning even cover that doesn't use the edge. So just delete the edge and suppress U to get GU FU. What I mean by that is now U is a vertex of degree 2. So suppression of that vertex, you just delete U and add an edge between its endpoints. And now you have two cases. Either you can path through the edge FU or you don't path through the edge FU. If you do, then you have a savings of delta, but since we don't include the cycle and that delta, you have to add 2. And if you don't use that edge, then when you lift it up to an even cover of GE, use an isolated vertex, and that has a cost of 1 in the excess. And so, since assuming that delta hat's greater than 3/2, this implies delta GU FU is equal to -1/2, and delta hat is also equal to 1/2. So it's an extremal case we've previously talked about, and we don't understand what that is. So it implies it's a minimal rooted theta chain. Okay, so the second case kind of reduces to the first case, since we understand the first case. Right. So, I mean, okay, that's roughly a high level view of the main theorem. So I'm going to briefly talk about how to get an algorithm from this proof. So with our full characterization, we can determine exactly when these delta and delta hats are equal to the extreme values. But for purposes of designing a quadratic time algorithm, it's not sufficient. If you do it naively, it's going to be exponential time, and if you do it slightly less naively, it will be cubic time. So you have to do a little bit of work to be able to estimate these deltas. And this is what our algorithm scan. So we want to efficiently estimate the extreme examples of delta delta hat without doing too much work. So what scan computes is an estimate, which we notate with big del instead of little del, and it's always bigger than the little dels. And how it estimates is if GE is a rooted theta chain, then it gets -1/2, 1/2. If GU FU, recall that GU FU is obtained from G minus C, suppressing U, then it's -3/2, 3/2, and it's -1, 1. And this is this is delta GE when G minus C is 2 connected, I should say. And so identifying these graphs can be done in linear time, and right. And so what we proved, and theoretically in the graph structural argument, is that we understand the structure well enough that we understand these estimations are going to be okay. Essentially, like so we had to get insight on the extremal examples to be able to design the quadratic time algorithm. I don't see how, off the top of my head, we could start with the algorithm and then show it works. We had to prove some theory before we could get to the quadratic time. And so I'm going to just briefly flip through the algorithm. I don't want to dwell too long on it. If you are curious, the preprint should be on the internet by the end of the week with the full algorithm details. So this is our scan algorithm. This is probably the most important part that required the most insight. Once you had the nice way to scan, unrolling the proof into an algorithm was fine at that point, but we had to understand exactly when things go bad, be able to estimate. And so if you browse through this, DFS is a depth first search. So all we're doing is scanning, our way to scan is by doing a depth first search and understanding when the graph is disconnected or connected. The line 2 here is when G minus E is 1 connected. That is when GE is a closure of a chain. And that handles it, the chain case, and the rest handles when G minus E is 2 connected. Okay. And so here is our main algorithm. I'll just emphasize on line 18 and 20, we have to run a subroutine. So at first, the line 1 checks if it's a trivial case, if it's a loop, it shows a single vertex with an edge. Otherwise, it determines if the graph's a chain and then runs the algorithm recursively on each of the chain blocks, how you would imagine it would work. And if it's not, if G minus E is 2 connected, then it has to run these 2 subroutines, which I'll briefly cover now. Okay, so the first one is easier. It's EC hat, and it's just asking for a spanning even cover that avoids the edge, and so it just reduces down to GUFU as we've seen before, and you just recursively call the algorithm before. So EC is the even cover. It finds an even cover that uses the edgy, and it has 3 inputs on the 3rd input here, depending on what scan sees. And depending on what scan sees, it tells you roughly what the graph looks like, and it does 3 different things in each of the cases. This case handles when it's a rooted data chain at an edge E. Second case is the hard case. This is the core of the main theorem, and it essentially follows what we did in the main theorem. Besides on line 12. Line 12 has a subroutine, which we called subroutine because we didn't have a better name. And that part was a little tricky because if you didn't do it carefully, you would have an exponential time. So we had to do something a little clever to make sure it's polynomial. The subroutine's here, and it's essentially an algorithmic version of one of the key lemmas of the proof, but done in a careful way. So it doesn't recurse. There's a nice way to do it. And here's the final case of finding a spanning even cover through an edge E, but this is the case when it's a minimum theta chain. Okay. Right. So again, in summary, we let G be a simple 2 connected subcubic graph. Then we've bounded the min excess, and we've characterized exactly when this inequality is tight, and we can find the spanning even cover in quadratic time. And recall that there's a correspondence between excess and the minimal length of a traveling salesman walk by some linear shift in terms of n. And so this is the corollary is actually what we care about. And so everything passes through. And as a corollary of the corollary, we get a 5/4 approximation algorithm for cubic TSP. And so for, again, open questions, the better approximation ratio for cubic TSP seems possible. But since there's infinite amount of graphs where, okay, our results shows that any graph has a TSP walk of length at most this, but since there's an infinite family of graphs that obtain this bound, to get a better approximation ratio, you would have to somehow lower bound the optimal and have an understanding of when the TSP bound is higher than normal, and that would somehow yield a better approximation ratio. So in terms of like getting an approximation algorithm by simply just bounding the length of the minimum TSP walk, this is it for cubic graphs, so we're gonna have to do something new now. And then of course there's graphic TSP and metric TSP. All these is still very open on like what exactly is. There's still gaps in the approximation ratios. And of course, getting better bounds for graphic TSP is still wide open. Okay, that's all I got. Thank you.
Awesome. Thank you so much, Michael. Let's do a round of applause if everyone can please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. Awesome. All right, does anyone have any questions?
Is it possible to apply this notion on hypergraph, or we use one graph, family of graph with common vertex or something like that, weighted graph, or using subcube? You use subcube, we can substitute it with other classes of graphs.
Let me try and answer the question. I think so. I guess metric TSP is like the main thing people care about, and I do think there is some type of result in the literature where if you can get a nice approximation ratio for regular graphs where you allowed multi-edges, that would extend the metric TSP. Does that answer?
Yes, but we can apply in hypergraphs. You use simple graph, ordinary graph, yeah.
Oh, you're asking for about hypergraphs.
Yeah.
I have not even thought about that. I would not know anything about TSP for hypergraphs.
Family of graph. What about family of graphs with common vertex? We use one graph. So if we have family of graph with common vertex, simultaneously, this result could be possible for example, family of cycles, family of path.
I'm not sure. Maybe we should talk about offline on it. Sorry.
Okay.
I was actually just wondering about, so the 2016 paper, they conjectured this result, but then had a different bound. What was the main thing, I guess you guys did that was different?
Okay. So one of the main reasons people like the cubic TSP is you can get a distribution on the edges where you can find like a matching where each edge has like equal probability of being in the matching. So one of the common strategies for a lot of these cubic TSP papers is to use that property to build the walk in some sense. So what they did is they used some structural graph theory to argue that the girth of the minimum counterexample is 5 or 6 and maybe some additional properties with that. But at that point, they got stuck. And then they did this matching argument, and that has rounding and probabilities, and the best they could do was like 9 sevenths. Our result's different in that it's purely structural graph theory.
Okay, yeah, thank you. Are there any other questions for Michael? Okay, maybe I'll end the recording there and then we can have some informal discussion. Thanks again, Michael.